In this lecture, we will be discussing about frying, pasteurization, sterilization, and milling process. The outline of this lecture will be as follows. We will be discussing about the frying, pasteurization, sterilization, and milling processes. What are the principles and working of these processes? What are the different equipments or plant level setup they use for these processes we will be discussing. Then we will be discussing about its utility applications and some of the latest advancement going on this field we will be discussing. So let us start with the food frying. So the primary objective of processes like baking, roasting, frying is to transform the food into a product which is having better quality. It is a value added products and they get the better prices. Frying contribute to the short-term stability of food by means of heating and drying. Basically, it helps to extend the shelf life of the food materials. The long-term preservation by combining with other preservation methods is also possible. There are different types of frying we use. First is called pan frying. This is applied to flat, wide, and relatively thin piece of food, such as patties and fillets. Food is cooked by contact with a small amount of hot fat, usually on one side and without any agitations. Then stir frying is done. So in stir frying, small to medium sized food particles are rapidly cooked in a small amount of very hot fat with the constant agitations. Then deep frying, in the deep frying, food particles are immersed in hot fat or oils. So here heat transfer occurs uniformly over entire surface of the food materials. We can see the examples of puri making or jalebi making for deep frying. There is a health concern over deep fried products because during the cooking there are some chemical compound formed and there are some other changes also which is badly affect the health. So that we will be discussing in this section. So both vegetables and animal origin fats is used for frying, and this long time heating, prolonged heating at high temperature in presence of moisture causes hydrolysis, and due to that there is increased temperature. There is oxidation, formation of cyclic fatty acids, and polymerizations. So these changes have adverse effect on food safety. It is important to reduce the occurrence of these three fatty acid formations, oxidations, and cyclic acid formation and polymerization. So that can be reduced by the proper choice of fat, frequent changing of oil in fryer, and avoiding too high frying temperatures and minimizing fat uptake by the product. There are some health implications of frying, like acrylamides issues. This acrylamides is a substance found when these estrogens react with reducing sugar at high temperatures. So it is suspected to cause cancer, so it is quite dangerous. There is starch containing food that have been subjected to high temperatures seems to main cause of cancer. Also, such that's the another challenge to address during the food frying process. So another topic is pasteurization. So it is used to kill microorganisms that are relatively low, that have low thermal resistance, that can sustain they cannot sustain high temperature, they will be destroyed. So it involves killing particularly vegetative microorganisms, and those vegetative microorganisms are not heat resistant spores. Heat resistant spores particularly we kill in sterilization. The purpose of pasteurization is pasteurization is relatively mild heat treatment, and in which food is heated to less than 100 degrees Celsius. It is widely used throughout the food industry. It can be used to destroy enzymes to inactivate their activities. It can be used to destroy relatively heat sensitive microorganisms, and it is used to extend the shelf life of food materials. There are different types of milk pasteurizations. We call like 63 degrees Celsius for 30 minutes. Time temperature combination we call LT process. Low temperature long time process. If we use 72 degrees Celsius for 15 seconds, we call it high temperature short time HTST process. So there are further given examples of HTST process like 89 degrees Celsius for 1 second, or 90 degrees Celsius for zero point 0.5 seconds, 94 degrees Celsius for 0.1 second, or 100 degrees Celsius for 0.01 second. That is a flash pasteurization. There are two groups of microorganisms that survive pasteurization temperature used in milk: uh, thermoduric and thermophilic. Thermoduric organisms that can survive exposure to relatively high temperature but do not necessarily grow at these temperatures. Examples: Streptococcus, Lactobacillus. Then there are thermophilic organisms that not only survive relatively high temperature but they require high temperature for their growth. There are different methods of pasteurization. One is a batch process and other is continuous process. So batch process are also called holding method. So in this method, every particle of the milk must be heated to at least 63 degrees Celsius and for at least 30 minutes. So this is the old techniques. Nowadays, due to its commercially not viable, not used much. Then comes a high temperature short time HTST process. So in this mess, heating of every particle of milk is at least 72 degrees Celsius and holding for at least 15 seconds is done. It is carried out as a continuous process. Then ultra heat treatment, UST sterilization treatment, this can also be performed using high temperature and short time like 1 second for 135 degrees Celsius temperatures. The typical equipment employed for STST method include heat plate exchangers, holding tube size to ensure correct treatment time is achieved, then holding tanks for storage of raw and pasteurized milk, then balance tank to assist in maintaining full flow and to take returned milk if temperature is not achieved, and it has a control and monitoring system which we can see in this diagram. So in this diagram, it is showing a pasteurizing using a plate heat exchanger. So we have raw milk balance tank, then we have hot water pump. So from balance tank, milk is taken to via milk pump to the regeneration section, then to heating section. So you can see there is steam supply, and that steam supply is having direct contact with milk, and it is transferring its his to milk via it is in flat heat exchanger. So you can see this black line here. So this is pasteurized milk, and it is taken to after pasteurization regeneration section. During regeneration section, there is a counter flow of raw milk and pasteurized milk. This transfer it, and it's some energy saving. So after that, it is taken the cold water. So cold water, somewhat temperature is reduced, then it taken to chilled water. Much temperature is released, like it is bring to the 5 degrees Celsius. So this is how the pasteurize work. Then next process is sterilization. Sterilization is controlled heating process. It is used to completely eliminate all living organisms, including thermoresistant spores in milk or other foods. It can be achieved by moist heat, dry heat, by filtration, by irradiation, or by chemical methods. The aim of sterilization is the destruction of all bacteria, including their spores. So it is more severe treatment, and it makes sure that all the microbes have been killed. So that is why you can keep sterilized milk we can keep for longer time even at room temperature. That sterilization process here, food product is filled in sealed container which are exposed to temperature more than 100 degrees Celsius. The temperature more than 100 degrees Celsius may be ranging from 110 degrees Celsius to 120 degrees Celsius depending upon the type of product, and here heat must reach inside the product are kept for defined period of time at temperature level required for sterilization. It is depending on the type of product and size of the container. Sterilization process in canned product can be subdivided into three phases. Phase 1 is heating phase, and here heating medium is water or steam is used. Product temperature is increased from ambient to required sterilization temperature. Then holding phase, here temperature is maintained for a defined time. Then cooling phase, a temperature can be decreased by introducing cold water into autoclave or chilled water. So this is the set of equipment. We call it autoclave or retort. So here you can see this open vessel. Here I can fill the cans, and once everything is loaded, then it is locked, and then steam is filled, and that steam will help to do the sterilization. So this is the diagrams for continuous hydrostatic sterilizer. So here you can see the can feed, which is raw materials which has to be sterilized field. Then it is bring a flake. It is via that it is taken to the preheat section. So in preheat section, like it is having temperature 82 degrees Celsius. Then initial primary heating is done, and then it is taken to the hot section where the uh, temperature like 110 120 degrees Celsius. Then steam chamber temperature increase from 150 to 129 degrees Celsius. Then further it's for some time when it take its sterilization is done. After sterilization, it is taken to the air cooling section where temperature is reduced. It's bring to only 93 degrees Celsius. Then it have water sprays. There much more temperature is reduced. And finally take the cooling bath. In cooling bath, further temperature reduction is done, and finally it is can discharge is done, which is sterilized and temperature also reduced. Now another important topic is grinding or milling. So in day-to-day life we use lot of powder, so that is achieved by this. unit operations. So grinding is a process of size reduction of solid materials by the mechanical actions. So these are the two types of grinding. You see, one is dry grinding, like we have edible flours, this powders. So here, if the moisture content is less than 16%, we call it dry grinding. And if the moisture content is more than 16%, like we have paste, butter, coconut paste, so that we define as wet grinding. So there are two groups. Now, the application of grinding. This is the perhaps most extensive application of grinding in food industry, particularly milling of grains to make flour. But it is used in other sectors also, like grinding of corn for manufacture of corn starch, grinding of sugar, milling of dried food such as food powder for production of bread, cake, biscuits. Another important application is spices grinding. The mechanism of grinding is that the grinding is achieved by fracturing the materials. And for efficient grinding, every energy applied to the material should exceed by a small margin as possible to the minimum energy needed to rupture that material. So that is the conditions. So what is the minimum energy required for rupturing that material? It should little bit higher than that to achieve the breaking of that particular full materials. So when we apply the energy, there is stress action by mechanical moving parts of the equipment of the grinder. So here time plays important role in fracturing process. It appears that material will fracture at lower stress concentration if this can be maintained for longer period of time. Energy required depend upon the hardness of materials and also upon the tendency of material to crack its friability. So there are different types of mechanism, or we say acting forces works in grinding. So first we call shearing force or attrition force, which we see in particularly chakis where traditionally they use and they grind the wheat and ragi or bajra or jar. Then impact force, we particularly see the example of hammer mill. Then compression force and crushing and impact force we see in peel mill, and then shearing force we see an example of fruit cutting. So there are different grinding equipments which we use. So major two categories: crushers and grinders. So crushers are the equipments where major action is compressive, breaking large pieces of solid material into small lumps, whereas grinders combine shear and compact force with compressive force and finally reduce the power feed materials into powder form. Grinding is not like a novel or recent advancement. We use from ancient time grinding operations in our day-to-day life food preparations. There comes a description about the grinding in holy scriptures like Srimad Bhagavatam. There it's mentioned that the 5,000 years ago when the Lord Krishna advented, when the Lord was a child, mischievous child, he used to break the butter pots and feed the butter to the monkeys. So me Mother Yashoda, she tried to bind the Lord Krishna to mortar and pestle. So the thing is that the description is the mortar use of mortar and pestle. So they used to use to grind these spices, and we see now in the town or home set. Still now in home we use these kinds of stone made mortar and pestles to make the powders. But slowly now it is the modern equipment replacing them. So these grinding equipments, the type of mills may be traditional mill, hammer mill, roller mill, colloidal mill, fixed mill, ball mill, edge runner mill, and distributed mill. So these are the few examples of the different types of grinder. The edge runner mill we use for making the powder of different types of herbs and spice, in particularly Ayurvedic preparation of different powder for making tablets, capsule, and all. Then pin mill, we see the different pins, and when these grinders operate, these pins rotate and by the force of impact or shearing or compression, they grind the materials. Then we have this jaw cursor already discussed, then this gyratrix. So even now also you will see in a village setup they use the coconut and from coconut they extract this oil, coconut oils and they use. So nowadays this may be earlier it used to be operated by animals, but now may be replaced by the electric operate. They use electrically operated gyratory cursors. So next is this hammer mill. So you see the feet and then attached hammers, and at the bottom the sieve attachment, and there we get the finally fine powder. And another is the plate mill. So we have these circular plates that hit the materials, and it rotates, and we get the fine product. Then we have roller mill. So the two rolls are there, which is moving in opposite directions, and we have input and finally getting the cursed materials as output. And it have different on the rolls. There are grooves, and the speed and their direction decide about the particular size reduction operation. So both rollers rotate at the same speed, then there is a compression as primary force. If they are rotating at different speed, then there is shearing and compression are primary forces. If rolls are grooved, a tearing or grinding component is introduced. The coarse grooves provide less size reduction than fine grooves do. One grinder we call ball mill. In ball mill, one important aspect is critical speed. Critical speed is a speed in which these balls starts rotating along with the equipment and there is no grinding. So this need to be avoided. So this conventional grinder, there are certain drawbacks and challenges like high heat generation, introduction of tensile residual stress, less tool life, oxidation, clogging, gumming of meal, loss of volatile oil in spice grinding. So all these problems are faced in conventional or traditional grinders. So to overcome all these problems, there is a novel approach called cryogenic grinding is used, and this is the setup which has been developed by Dr. K.K. Singh and Professor T.K. Goswami at IIT Kharagpur. So this is the setup. We will be explaining this later on. Let us first understand what is cryogenics. This word cryogenic originates from the Greek word cryo, which means creation or production by means of cold. It's deal with low temperature as low as below minus 150 degrees Celsius. Cryogenic is the study of low temperature and behavior of material under these low temperatures. A person who studies elements that have been subjected to extremely low temperature we call cryogenicist. There are several cryogenic liquids like nitrogen, helium, neon, argon, krypton, hydrogen, methane, or liquefied natural gases can be used as a cryogen. The liquid nitrogen is most commonly used. Cryogens are stored in vessel called Tivar flask and these have very good insulation. So these different cryogenics become liquid under different condition of temperature and pressure, but all have two properties common. They are extremely cold and a small amount of liquid can expand to very large volume of the gas. So these cryogenic are extremely low temperatures produced by using substances called cryogens such as liquid nitrogen and liquid helium. All cryogenic liquids are gases at normal temperature and pressure. So these gases must be cooled below room temperature so that we can liquefy them and then we can use them as a cryogen. Like we have a very low boiling point like 150 degrees Celsius. So let us talk about the liquid nitrogen. So nitrogen gas is the major proportion of atmosphere. It's now the 78.03% by volume. It is another good thing is that it's inert. It is colorless, odorless, non-corrosive, non-flammable liquid. It is extremely cold. It's having very low boiling point like minus 195.8 degrees Celsius. And when it is in liquid form, it's exactly look like water, and it's a volume expansion is very high. Like 1 liter of liquid nitrogen evaporate to form 682 liter of nitrogen gas. That is why it is quite challenging to store it because it keep on evaporating. We cannot make a 100% sealed container and put it in that. So there is a Sir James Dewar. He born in 20 September 1982 and died in the year 27th March 1923. He was a Scottish scientist. He was a physicist. He has invented this Dewar flask. So you can see the design of the water flask. It have vacuum, it has silvered surfaces, and it have inside we can keep hot or cold liquids. It can be stored for longer time because it's a very good insulation. So this is the Diwar flask we use for storing the liquid nitrogen. And this is this is the scientist who also has first time liquefied the hydrogen gas. Now let us talk about the cryogenic grinding. So in this cryogenic grinding, we call it also as the freezer milling or freezer grinding or cryo milling. It's act of cooling, chilling a material so that it become brittle and then reducing it to smaller size particle by grinding operation. Also a method of powdering herbs at sub-zero temperature ranging from minus 18 to minus 57 degrees Celsius. All the materials imbrittle when exposed low temperature. It utilises cooling effect of liquid nitrogen to imbrittle materials prior to or during the grinding operations. That's important. Normal grinding process which do not use a cooling system can reach up to 93 degrees Celsius during the grinding. So this is quite high temperature. So, at that high temperature, it loses its volatile component, color, oxidation. So all those changes reduce the quality of the material. This high temperature can reduce volatile components and heat sensitive constituents in herbs, spices, or food components. But cryogenic process does not damage or alter the chemical composition of plant in any way. The material which are elastic in nature, having low melting points, low combustion temperature, sensitive oxygen can be ideally machines by cryogenic grinding process. So there are several applications like grinding of steel, thermoplastic, thermosites, adhesives, excisions, explosives. Our interest is in the field of food materials like spices. So in spice grinding, so this the spice is very important constituent of our Indian foods because we produce a lot of spices in India, and from ancient times we see the history that we have used to do export of lot of spices to other countries also. So not only in household food, also it's in the hotel, restaurant, food processing industries we use it. Particularly examples pepper, cinnamon, chili, ginger, cumin, nutmeg, clove. They have characteristic taste, aroma, and medicinal value, and we produce a lot of them, and we have a lot of its economical incentives. These characteristics qualities are essential in them to have their value as the spice, and these qualities exist in them due to the presence of essential oil within it, holding boiling point below 50 degrees Celsius. That's important, but we discussed that normally conventional grinding temperature may reach up to 93 degrees Celsius, and which may deteriorate this quality of grinding. So problems like loss of essential oil, clogging, gumming of mills, so this creates a lot of hindrance in grinding operation, or there may be oxidation or related degradations due to intimate contact of oxygen. It may do oxidation, rancidity of the materials. So to all address all these problems, this cryogenic grinding system has been developed and it is suggested. So in the cryogenic grinding system, the important components are two units. One is pre-cooling unit and then grinding units. So in pre-cooling, before grinding, we could reduce the temperature of materials. We bring it low temperature and then take it for grinding. In the grinding unit also, we can apply liquid nitrogen and we reduce the temperature. So in pre-cooling, pre-cooler is a cooling device made up of the screw conveyor enclosed in a properly instituted barrel. We will see that also in our laboratory setup. A system to introduce liquid nitrogen into the barrel and thereby providing refrigeration, liquid and cold gas within the system. The function of cryogenic pre-cooler is to remove the heat from the materials before it enters the grinder. So this pre-cooling unit is consists of a screw conveyor assembly, an air compressor, a liquid nitrogen lever, a power transmission arrangement, and control panel. Reduce the temperature of sheet below its brittle point as well as freezing point of its oil before it's enter the grinder. The temperature of pre-cooler and feed rates to grinder are controlled to minimize loss of quality of final powder materials. Consumptions of liquid nitrogen. Operation costs are important consideration and matters of concerns for a cryogenic pre-cooling system. Liquid nitrogen loss can be minimized to a greater extent by proper consideration of design and insulation of pre-cooler. So there are several engineering consideration, the retention time, appropriate insulations, and easy in dismelting and cleaning, and reduction in the cool down losses. So this is the setup or grinding unit. So its operation of grinding was performed by impact and attrition mill in this grinder. The grinder was operated by an electric motor. It's have electric adjustment operate. It's ground powder collected in collector pan from an outlet and nitrogen vapor let out. So this is the showing the flow charts. What are the different steps involved, like loading in a hopper through vacuum conveyor, then feeding in cryogenic screw conveyor, then chilling of spices with liquid nitrogen, then feeding of spices in grinder, then grinding of spices at low temperature and invert atmosphere, and then extracting low temperature from ground spices, and finally the powder is packed. So this is the setup. So we have like feeding of manually cleaned material to be ground. So we have ground granulated feed material. So that is like in cooling conveyor that is taken this through the cooling conveyor to the grinding mill, and also we have this liquid nitrogen tank. From there we use this liquid from storage tank in sprayed cooling conveyor section, and this is along with that material to be grounded. It is taken to the grinding mill. The grinding takes place. So vaporized liquid nitrogen is sucked by a centrifugal blower and fed back to the mill, and cyclic process is continued, and in the grinder the finally ground powders is collected. So this is a schematic diagram for cryogenic grinding system. There are several salient features of this novel approach. So it helps to high retention of essential oils or volatile oils because it is operating low temperature. The problem of oxidation and rancidity is addressed, and it gives increased throughput and power saving. It's basically energy saving. We get finer particle size, that is reduction in microbial load because we operate at low temperature, and some of the dormant microbes will be destroyed. Then possibility of fine grinding of difficult spices, particularly which have a lot of oil like ajwains, fenugreek, those kind of spices we easily can grind here. So this is showing a comparison between the traditional grinding and cryogenic grinding. Traditional grinding, there is a lot of heat generation inside the grinding mill, whereas it is operating at very low temperature or less than 0 degree Celsius temperature. In traditional system, the heat which is developed during grinding leads to have some of the problems, leads to maybe release of greasy oils, or which may leads to blocking, whereas there is no loss of volatile components. So traditional system lot of energy consumption, whereas cryogenic grinding system energy consumption is less. So traditional systems with high capacity motors required to grinding, whereas here low capacity motor can be used. So in traditional system we don't have control on the particle size, but in cryogenic system we can keep the particles as per the requirement. So as for the a lot of research going on this field, and if someone interested can go through this latest research on cryogenic grinding. This is the another study and comparative study on ambient and cryogenic grinding of fenugreek, black pepper seed using rotor mill, ball mill, hammer mill, and feed mill. And here this is another article on flow characterization for black pepper. One can go through. So there are certain precautions which one need to take care during the grinding, like while handling the cryogenic liquid. So there should be take care because it may create skin or eye hazards. So there should be use of proper tools and equipments and apparatus to avoid such hazard. There can be cold embrittlement. So they should use rubber, plastic, or carbon. So those may be brittle, very brittle at reduced temperature, and these materials may create some problems. So one should be careful while handling. And there may be oxygen enrichment, so that may leads to some flammability or maybe fire hazard and all. So that should be avoided. So the care should be taken, precautions should be taken. Someone should be familiar with the hazard associated with the cryogen use. One should work in open and well ventilated locations. While operating, one should always wear safety goggles, face shield, and appropriate oxygen gloves. One should examine container pressure relief valve for a sign of defect. Ensure that all the equipments containers are free of oils, grease, dirt, or other materials which may lead to the fire hazards. So that should be care should be taken. Thank you very much. With this we conclude this lecture here itself.